Hi, welcome back, Allen High School Pre-AP kiddos. What we're going to be looking at now, we're still focusing in on liquids. We're going to be looking at the changes involved in going from the liquid phase to the vapor or gaseous phase. Now, let's review a few terms that we need for this. If we are at the boiling point, okay, the boiling point, let me define that in just a second, okay? Let me hold off on that. That's called boiling. So it's the vaporization. It's going from liquid to gas at the boiling point. That's the vaporization. If it is below the boiling point, we really don't call it vaporization anymore. We call it evaporation. So vaporization is at the boiling point. Evaporation is below the boiling point. Now, because when we go to liquid, from liquid to gas, we are breaking IMFs, and it takes to break intermolecular or any forces of attraction. This is an endothermic process. It requires an input of heat and energy to weaken intermolecular forces. Now, remember, vaporization takes place. What happens is molecules can escape from the surface of the liquid. And so if I have a closed system, so let's say this is kind of a beaker and it's a closed system, some water is naturally going to escape, whether it's evaporation or vaporization, which is what I prefer. Vaporization's at the boiling point, evaporation below. Some will escape and break those intermolecular forces, and you'll start forming gas molecules. Now, that gas molecules can hit the side of the container when that force per unit area is called a pressure. So that's called the pressure of the vapor. Last unit, when we looked up the vapor pressure of water at different temperatures, when we collected a gas over water, this is what we're talking about, is the vapor pressure of water. Now, if it's a closed system, we reach a point at which the rate of condensation is equal to the rate of evaporation. So we would set up a rate of condensation is equal to the rate of vaporization or evaporation. And when that happens, we're going to be setting up an equilibrium. And when that happens, we can report those vapor pressures. Okay? So, the liquid molecules need enough energy to break their intermolecular forces and reach the pressure there. Okay? Now, the vapor pressure at any temperature, all liquids have some evaporation happening. And this is because there's always going to be some molecules that have enough energy just because of their kinetic energy to leave the liquid state. That's what's happening in here. This is what this picture is trying to show, is this is your liquid and this is your gaseous or vapor phase. Okay? And some will break. So that means that all liquids have a vapor pressure. Okay, the vapor, as temperature increases, so as I increase the temperature, you're going to increase the kinetic energy of the molecules, and pretty soon they'll be able to break those intermolecular forces. So you're going to increase the number of intermolecular forces broken. So you'll increase the moles of the vapor or the gas, and that in turn is going to increase the vapor pressure. And that's why we saw those temperature versus vapor pressure tables for water last time, because vapor pressure is temperature dependent. So as you increase temperature, the vapor pressure of a liquid will also increase. All right, now let's see here. Evaporation rates, if left alone, it's going to vaporize of its own accord. It's going to evaporate. Now, if the evaporation rate is all going to be dependent on the intermolecular force strength. Okay, so if we have, for example, water molecule, two water molecules, the force of attraction between two water molecules is very, very strong. So that's going to be a very strong attractive force. So it's going to evaporate more slowly. Not only that, it's not only going to evaporate slowly, it's going to evaporate less at any given temperature. And that's because it has strong hydrogen bonding. So as you increase the strength of your intermolecular force, you're going to decrease the moles of gas, because fewer molecules can go from liquid to gas because the force of attraction is too strong. And so you'll actually decrease the vapor pressure. Now, conversely, acetone evaporates fairly readily. It is polar, but it still evaporates fairly readily because it has actually, it's polar, so acetone is polar. So acetone has dipole and London dispersion forces. Water has hydrogen bonding and London dispersion, but it's the hydrogen bonding that dominates. Okay. Now, these dipole attraction forces and the London dispersion forces, they don't need as much energy to break apart into gases. So that's going to lead to lower boiling points, and it's going to be a higher vapor pressure. So let's go back to our example. I'll do the acetone in red. So here's one acetone molecule. Here's another acetone molecule. Now this time we have dipole and London dispersion forces of attraction, and they're going to be weaker. So those attraction between the two molecules are weaker, and so as we decrease the intermolecular force strength, more molecules will go to gas phase, so I'll get more moles of gas, and I'll have a higher vapor pressure at any given temperature. So the vapor pressure of acetone is going to be higher than the vapor pressure of water at any given temperature. Now, substances, liquids that evaporate readily, if you think about gasoline, if you're filling your tank and if you ever spilt a little gasoline, it goes to the gas phase very readily. We call those volatile. That's a really important vocab word. You would even use that word like if you talk about somebody has a volatile temper. It means they anger very easily. A volatile gas is one that goes to the gas phase very readily. Okay, now, if we've got vaporization in a closed container, what we reach, and I talked about this earlier, is a phase equilibrium. Where the rates of condensation and vaporization will be equal. And so even in your water bottle, you're going to see some condensation on the edges, and some will evaporate, but as every molecule that evaporates, another one condenses. Now, earlier I mentioned, good, we'll talk about that later. Earlier I wanted to come back to this boiling, and I said I'd come back to it. A substance boils as soon as the vapor pressure is equal to the pressure of the atmosphere. That's the definition of boiling. So as soon as it builds up enough vapor pressure, especially now we're talking in more of an open container, but as soon as that vapor pressure of the liquid equals the atmospheric pressure, the substance will boil. And that's how we define boiling in terms of vapor pressures. All right. Got quite a bit more to do in this unit, so we will be forging ahead, and until then, this is signing off.